Hello, everyone. My name is Nikita,
My name is Vincent.
And I'm Crystal.
and today we'll be talking about the augmented fixation of implants for osteoporotic femur fractures. So, here's a brief table of contents that will tell you what exactly we'll be covering during this presentation. So, understanding osteoporosis. So, osteoporosis is a silent bone disease that is characterized by low bone mass and the structural deterioration of bone tissue, and it is normally caused by hormonal changes, poor early nutrition, or lifestyle habits, along with prolonged uses of SSRIs. And it is estimated that men lose up to 5 to 15% of their cortical bone mass, while women tend to lose 25 to 30% of their cortical bone mass. So, the incidence and burden of osteoporosis. Osteoporosis leads to the increased bone fragility and risk of fractures, particularly in the hip, spine, or wrist areas, because those are the areas that take the most amount of gravitational forces through everyday activities or if they were to fall. And if a patient were to suffer a fracture, then there is an increased 86% risk of fracturing the same side again, which also contributes to an increased mortality rate of 27% during the recovery process. This leads to around reduced quality of life for 40% of the patients who require 24/7 assistance, which makes osteoporosis a very expensive disease.
So for the market analysis, the customer base of this method include elderly patients, athletes, military workforce, and blue-collar workers. Osteoporotic fracture uh, reportedly costs $17 billion each year and estimatedly raised up to 40 billion by 2019. The largest markets for osteoporosis treatment are China and India, where most 80% of the patients located there. The standard treatment used the implantation of the bone screw and blades. Another complication for osteoporotic patients include microfracture around the implant site, the implant load-bearing failure, the reoperation in 23% of cases. Also increase the patient mortality in refracture cases, particularly hip fractures. That's a gap from the current methods involve the metallic screw to adhere the bone plate. The implant screw cause microfractures, which contribute to weaker bones with multiple potential points for future fractures. There's a need in a secure fixation to address fractures.
So, for our project, we referenced several literature reviews, and the first one that I'm going to review today is on the testing that was done on human osteoporotic vertebrae models that was tested for screw pull-out strength without and with PMMA. And here's an image that shows the volume and shape of the PMMA that was injected, and the volume injected was 1 centimeter cube and 2.5 centimeter cube in spherical and cylindrical form. In average, the pull test results increased by 57% for normal bones and 137% for osteoporotic bones. The second literature that we studied was the femoroplasty conducted on osteoporotic femur heads. And in this one, they injected around 40 milliliters of composite bone cement, and the results showed that there was a 43% increase in failure load handling and 187 increase in energy to failure rate. And the image here shows where the PMMA was injected, while the arrows show where the screw was inserted into. And one of the first things that we had to face was to simulate an osteoporotic bone. And then we found that the study showed that there were multiple molarities of the diethylene diamine tetraacetate acid, or more commonly known as EDTA, was studied for the decalcification of human bones. And studies conclude that around 0.5 molar of EDTA during decalcification increases the porosity without damaging the cell structure of the bone itself. And an image at the bottom shows the decalcification of a rat skull at various temperatures for a total of 10 days. And the image on the leftmost here shows the completely decalcified incisor of a rat, which is colored through the use of the Von Cause and additional methods. And so our project objective this semester was to develop a method to secure fixation of the implant using osteoporotic bones with PMMA. And this way we would be able to obtain a stable fixation of an implant and improve the load-bearing factor of osteoporotic bones.
For materials, we're going to go left to right and I'm explaining which material and what it's used. So we're going to start with the pig bones. This is our experimental items. They're about 3 inches long. Then we have methanol used to remove any excess from the bone, hydrogen peroxide to decontaminate the bone, and a spic expand solution to sterilize the bone. Then we have phosphate buffer saline, PBS, to hydrate the bones. We have the 0.5 EDTA to decalcify the bone samples. We have rubbing alcohol to sterilize our workstation, and 25-liter containers for storage and process of samples. We have DI water to dilute the chemical solutions, a kettle used to control large quantities of water heating, number 8 size 1-inch stainless steel pan heads used to insert into samples for pull tests. We have the electric drill used to insert the screws into the bone, and the drill guide to stabilize drilling at perpendicular into the bone. We have expired PMMA used as our adhesive to inject into the bone, and to inject that we use the syringe. Next we have a scale to weigh the bones, the Instron tensile testing machine to conduct the pull test, and lastly a horizontal bandsaw to cut cross sections of the bone. For our methods, the bones were partially frozen, so we let this thaw at room temperature for about 30 minutes. We physically removed the external flesh. Then we submerged the bones into about 70 degrees Celsius water to soften the yellow marrow. Then we physically removed that as well. We submerged the bones into the 10% spic and span solution, also heated at a 70 degrees Celsius, and we attempted a physical removal of the periosteum layer on the surface of the bone. We soaked the bones in a 10% methanol solution to remove remaining biohazards. Here we have the methanol. In the middle is the hydrogen peroxide, which is used to remove any of the remaining biologicals. And lastly, we have the bones soaking in PBS until further use. For simulation of osteoporotic bones, we let this submerge into EDTA for 2 weeks to decalcify. We changed the solution every day for the first week, 50%. And then for the second week, we changed 100% of the solution, and for the remaining days of that week, we changed 50% of the solution.
So to determine if we were properly able to simulate osteoporosis, we measured the bone mass and volume displacement of the bones before and after EDTA submersion and used those values to calculate the density difference of the bones. And in this table here, you can see the top 5 bones that reached a density difference of closer to around 25%. And here is our project test matrix. So we have 5 healthy bones that went through everything other than the PMMA injection, 5 osteoporotic bones that also did not go through the PMMA injection. Then we had 5 more osteoporotic bones with PMMA that was used to study if the PMMA was injected properly into the bones, and 9 osteoporotic bones with PMMA that went through each of the multiple tests shown here. So for the screw insertion process, we first drilled a pilot hole using a drill bit that was smaller than our screw diameter, and then manually inserted the screw with care using a drill guide to minimize any fractures on the bone. And we aimed for the tip of the screw to be less than 1 millimeter through the compact bone. And for the PMMA injection, we drilled 8 pilot holes through the compact bone, stopping just above the endosteum layer as shown in this diagram here, and then injected PMMA using a syringe into those drilled holes and then placing excess PMMA on top of the holes, injected and compressed the PMMA down to create a sort of ceramic plate. And for the testing, we went through 2 separate ones. One was the imaging process, and the second was the pull-out strength test. For the imaging process, we selected the best spongy bone that had the for before and after EDTA decalcification. And then we captured images of the spongy bone tissue using the Vitsync lenses at 10 times magnification, and then those images were run through ImageJ to determine pore size. And then for the pull-out test, we secured the bone onto a customized fixture and had the screw attached to a L-bar as shown here, and then the test was conducted and the data collected and analyzed.
So for the before and after decalcified result analysis, we show you the bone sample 5. The first chart is the before decalcification, where the pore length go from minimum 0.004 centimeter to 0.07 centimeter with a median at 0.027 centimeter. And the chart here show actual decalcification process. Bone sample 5 has a pore length from the minimum 0.005 to 0.128 centimeter with the medium at 0.0335 centimeter. So there's a significant increase in the pore size before and after decalcification. And the figure 44 and 45 show the images of bone sample 5 before and after decalcification process.
In this video, we're going to show our healthy bone after doing a pull. We're going to show healthy bones for the pull test. At first, it's going to go at a speed of 32, then it's going to slow down to a normal speed near the fracture, and then we're going to replay that fracture section at a slower rate. Here in the images shows the healthy bone fractures near the implant site of the screw. In this video, we're going to show the osteoporotic bone with the PMMA injection. First, it's going to go at a speed of 32 again. It's going to slow down at the normal speed near fracture site, and then it's going to slow down. And then we're going to repeat that at a slower motion. And then these images show the osteoporotic bone with PMMA injection. It shows that there are fractures where the PMMA injection is near the fracture site.
So after conduct the experiment, we have the table compared to the literature with respected value. So 3 types of bones. Our result the healthy bones go from 1120 Newton to 1880 Newton compared to 800 to 1150 Newton from the literature. The osteoporotic bones without PMMA from 258 Newton to 718 Newton compared to 400 to 650 Newton from literature. And the osteoporotic bones with PMMA, the value go from 645 Newton to 1195 Newton compared to 600 to 800 from literature. And the chart here show the average pull test result from 3 types of the bones. The average holding power from of the healthy bones is around 1500 Newton. Meanwhile, the osteoporotic bones is 488 Newton, and the PMMA injected osteoporotic bones is 920 Newton. So from the data we collected, the result we get from the average holding power from osteoporotic bones is 488 Newton, and the PMMA injected osteoporotic bones is 920 Newton. At the conclusion, the preliminary experimentation showed that the Adhesion between the osteoporotic bones and the screw matrix increase the holding power by double with the addition of PMMA. For the future work, we suggest conduct more research on alternative bone cement material that has lower viscosity. Also design alternative implant screw with a core in the center for alternative bone cement intrusion. Also use a different section of femur for testing, particularly the head of the femur where there is more puncture tissue present for PMMA intrusions. Here's the appendix of material and the reference.
So for acknowledgements, we'd like to thank Dr. Guna Salvadori for advising us this whole year regarding our project, Dr. Keelis and Dr. Eric Bobo for providing additional advising. And with regards to bone cleaning and sterilization, we'd like to thank Dr. Lorna Pierce and Mr. Ryan Scott. And with regards to hazmat, parts design, and construction, we'd like to thank Mr. Neil Peters, Mr. Scott Gaudet, and Corey Simpson. Here are our signatures. And thank you for everything this year.
Thank you.
Thank you.